Hello, everyone. My name is Yuezhi Liu, a SEP scientist at Q-Chem Pleasanton. It's my pleasure today to introduce our speaker today, Yuezhi Mao. He will talk to us about projection-based quantum mechanical embedding methods in Q-Chem. Yuezhi received his bachelor degree in material science, material chemistry from Peking University in 2012, and he joined Professor Martin Heck-Warren's group at UC Berkeley and earned his PhD in chemistry in 2017. He then worked as a postdoc scholar in Professor Tom Markland's group at Stanford University. In this August, Yuezhi started his independent position as assistant professor at San Diego State University, where his group will continue work on the development and application of new theoretical methods. Yuezhi has contributed extensively to the features and code infrastructure of Q-Chem during his career. And the work has been recognized by the Michael Warmit Award in 2020. It has also presented twice in Q-Chem webinar series introducing the energy decomposition methods he had developed with other co-workers. A broadly used feature in Q-Chem for studying non-covalent interactions. As always, I would encourage you to post your question in question box in the GoToMeeting. Then I'll relay them to this Yuezhi at the end of the talk. Without further ado, I'm gonna turn this over to Yuezhi.
Okay, I hope everyone can see my screen okay. Okay.
Yeah.
Great. Okay. So today I'm going to talk about the projection-based quantum mechanical embedding method in Q-Chem. So at the beginning, I want to first clarify that these embedding methods are not developed by myself. So if you come to ask me, what is your embedding method? I will tell you I don't have one yet. So these methods, these projection-based embedding methods are largely based on the original development. These methods were originally proposed by Frank Manby and Tom Miller. And so this method was originally implemented by Daniel Lambert in Q-Chem based on the old SCF framework, and this was like introduced as a part of one of the very early webinars. But this original implementation did have some limitations. For example, for correlated wave function method embedded in DFTs, supported methods are only MP2 and the CCSD_T. Also, because it's in the old SCF code framework, the code was not maintained very well, unfortunately. So back in 2017, Junho and I, who were both graduate students in Martin Heck-Warren's group, we started this current new implementation as a late night / weekend project. And then after a while, we got a working code, but it was barely usable for anything. Then a former postdoc in Martin's group, Jerome, did make some important revisions to the code. So then we at least got like a DFT embedding working. But for wave function in DFT, it is still not very useful because we don't have a scheme to truncate the virtual orbital space. Then in 2019, Nick Mayhall's group published 2 papers, one on how to partition the occupied space and one on how to truncate the virtual space. So I realized that these are the methods we really need, and I implement this method in Q-Chem, and then we really have a fully functioning like a wave function in DFT embedding. Then Professor Thomas Yagao and his student might be the first actual users of this code. They did investigate a lot on the embedded EOMCC equation of motion couple cluster calculations, and they even further extended that to complex basis function calculations, which I will not really talk about today because I'm not an expert on that. But this new development has also been documented on the Q-Chem menu. And finally, I want to thank my postdoc advisor, Professor Tom Markland, and he did give me quite a few like collaborative projects, so in which I was able to use this like embedding code. So it was something I developed back during my PhD, but actually I got it. I used it for some applications actually quite a few years later. Okay. So Q-Chem as a comprehensive electronic structure package, it does offer a lot of methods for modeling the environment. This is quite important because the majority of chemistry actually happens in the condensed phase. So first we have implicit solvent models. And this was introduced by Professor John Herbert in one of the recent Q-Chem webinars. And so we have popular implicit solvent models such as PCM and Minnesota solvation models and so forth, and more sophisticated like a Poisson-Boltzmann model. These implicit solvation models are relatively easy to use, but they don't give you the atomistic details of the environment. So if you want to go one step further, to treat the environment explicitly, then you can do QMMM method. So Q-Chem does have some standalone QMMM functionalities, but those are quite limited. But Q-Chem do have interfaces with more established MM code, such as CHARM, GROMACS, and Ember. So there are some previous webinars introducing the Q-Chem CHARM and Q-Chem GROMACS interfaces, and the interface with Ember was developed recently by Professor Yihan Shao's group. In addition, Q-Chem also supports a few polarizable QMMM type models, such as QM effective fragment potential method, and also this is through the Q-Chem libEFP code interface, and through the interface with libPE, it also supports the polarizable embedding method. And if you want to go then another step further to treat the environment fully quantum mechanically, then we have Q-Chem has projection-based embedding. This is today's topic. And it also has frozen density embedding, which was primarily developed by Professor Weslowski's group. So as I mentioned, this projection-based QM embedding was originally formulated by Fred Memby, Tom Miller, and co-workers. So this method requires a partitioning of the entire system into a central part where interesting chemistry or electronic excitation happens if you are doing excited state calculation, and also the surrounding environment. So you have the system partitioned in this way. And then these two parts can be treated at different levels of electronic structure theory. So this method contains the atomistic details of the environment. It also takes a polarization effect of the environment into account, as well as the Pauli exchange repulsion between the system and the environment, which are some very desirable features that are usually missing in QMMM type of models, especially the fixed charge version of QMMM. So first, let's look at the formulation of this method. And So let's first focus on like a DFT in DFT embedding. So here, like I use fragment A to denote the active fragment and the fragment B as the environment. So fragment A is going to be calculated at a higher level theory in the presence of the in the environment of the provided by fragment B's nuclei and the electron density. So first, basically the method first do a calculation at the low level theory. So if we are doing like a DFT in DFT embedding, it can be hybrid functional in a pure functional. So we say we do a calculation in a pure functional, and then we get the total system density. Then we need to find a way to partition that density into fragment A's and fragment B's. And the sum of their electron density need to be the total density. And to satisfy that, we will need to enforce the molecular orbitals on A and B are orthogonal to each other. And after doing this partition, we use the high-level method to re-optimize fragment A's electron density, and then subtract that calculated using the low-level theory. So if you are familiar with like a onion type onion type Hamiltonian, this is exactly like the same idea, but now both the high and the low-level theory are like quantum mechanical methods. So if we then differentiate with respect to this like active system density in a high level calculation, we can get the effective Fock matrix for the embedding calculation. So the differentiation of the first term gives you this Fock matrix at the high level, and then the derivative of the next two terms will give you the embedding potential. So it will just be the difference between the low-level Fock matrix calculated using the full system density and just the active system density. Okay, and also to enforce the fragment A and the fragment B's molecular orbitals are orthogonal to each other. So the original method actually adds this like a scaled projection operator to the Fock matrix, and probably this gives the name like of this method called projection-based embedding. Okay, so usually this mu, this scaling factor, is a very large positive constant, like a 10 to the 6 or 10 to the 7 atomic unit. So this make sure that the molecular orbitals of fragment A and fragment B will not mix with each other in the embedding calculation, since otherwise this will be heavily penalized by this large constant. But in Q-Chem, we actually adopted a parameter-free approach, because this mu is, I mean, after all, it is a parameter. And so in Q-Chem, we use the parameter-free approach by just project fragment B's occupied space out of the full AO space. So we just do this and then diagonalize this reduced Fock matrix. And from the resulting orbitals, we can select the ones which are orthogonal to the fixed orbitals on fragment B. And those are the orbitals we need, like the occupied on the active fragment and also the virtuals. So there is one disadvantage of this energy functional, because so in this formulation, the embedding potential will depend on this active system density gamma twiddle gamma A. So that means in each iteration of the embedding calculation, you will have to update this embedding potential. So that will add additional computational cost, especially for DFT in DFT embeddings, that will be quite significant. So to avoid updating the embedding potential at each iteration of the embedded SCF, so people have suggested doing this linear approximation. So this is like doing a Taylor expansion of this original energy functional with respect to the gamma A calculated at the low level, and then truncate just at the linear order. So this now the embedding potential still has this like a fork matrix difference form, but now this gamma A doesn't have a twiddle anymore. It is fixed, and it is calculated at the low level and then get fixed. Okay, so in this way, the embedding potential can be computed at the very beginning and just keep fixed in the embedding calculation. So with this linear approximation, so here is energy functional and the Fock matrix for DFT in DFT embedding. And for wave function in DFT embedding, we can absorb this interaction between the active system density, twiddle gamma A interacting with the embedding potential. We can absorb this into the Hamiltonian of this wave function calculation. So this will be the energy we finally get with a wave function in DFT embedding. So now we have two questions to address. One is how to partition the occupied space, or how to partition the electron density to get gamma A and gamma B. And so the original method was adopted by the previous paper by Fred Memby, was using this Pepak-Mersey orbital localization. So they do the orbital localization for the canonical occupied orbitals obtained from the low-level DFT calculation, and then they assign localized orbitals with molecular population greater than 0.4. So if one localized orbital has molecular population greater than 0.4 of the active fragment, then it will be assigned to that fragment. And however, this 0.4 is a somewhat arbitrary parameter. And if there is no user interference, there is totally no guarantee that the number of selected occupied orbitals for this active fragment will match its number of electrons. So in Q-Chem, we revised this method a little bit, just by selecting the localized orbitals that have the largest populations on fragment A until we reach the number of electrons. However, this Pepak-Mersey localization is still quite sensitive to the employed basis set. So usually this method doesn't work very well when you have diffuse basis set, and especially when Q-Chem reports, we detect like a linear dependency in your AO basis set, then this method is going to break down. So in 2019, Nick Mayhaw and his postdoc suggested this subsystem projected AO decomposition SPADE method, and this is a simple parameter-free approach I highly recommend, although I haven't made this default yet. So this method, so let me tell you how this works. So first, we transform these canonical occupied orbitals into the orthogonal, the symmetrically orthogonalized atomic orbital basis by this is just by left multiply this S1/2, and then we select the rows because this is like a rectangular matrix. So you can select the rows corresponding to the active fragment A. Just pick the rows corresponding based on the tag of the AO basis function. Although they are orthogonalized here, we still assign tag atomic tags to these orthogonalized AOs. So we just select the rows corresponding to A, and then doing an SVD, single value decomposition. And then using the right vectors of this SVD, we can just select the first field, which the number should match the number of electrons for fragment A, and we just do this unitary rotation. So by doing this unitary rotation, so if you just take the full right vector of this SVD, you get, so the first NOA, like the number of occupied orbitals on A, will just correspond to the the occupied orbitals assigned to that active fragment, while the rest will go to the environment. So I do plan to make it as the new default, maybe at the 6.1 release. So with this method, we now have a partition of the occupied space. So we started from the canonical orbitals from a low-level SCF calculation, and we now partition the occupied orbitals into environment and the active system orbitals. And we also need a way to truncate the virtual space. That's the second question we need to address. This is extremely important for wave function in DFT embedding because the cost of a lot of correlated wave function methods increases very steeply with number of virtuals. For example, CCSD, the scaling looks like O square V to the fourth. So virtual actually is more important than occupied. And also, the truncation of virtual is more important to the reduce of the cost of this method. And it's also relevant in TDDFT in DFT embedding, which I will talk later. So that will basically reduce the dimension of the singles amplitude of a TDDFT calculation. Okay, so this is also a method from one of the two Nick Mayhaw papers. So this method we implemented in Q-Chem is called concentric localization. So it is able to obtain truncated virtual spaces with a controllable accuracy. So the idea, the spirit of this method is somewhat similar to the spade approach. So the first step is to project these full virtuals onto a user-defined projection basis for fragment A. And then by doing an SVD of the overlap of these projected virtuals and the original virtuals, we can select the first set of included virtuals denoted as C0. And then we can keep doing this. Then we can select a one electron operator, such as the fork matrix here, the fork operator here, and then we just keep calculating the coupling between the selected virtual orbitals and those excluded in this null space of the SVD, and we can recursively do this until we run out of virtuals. But the point is we can stop much earlier before we use up all the virtuals. So here we use this zeta number to specify how many these sets of virtuals are included. So with the current default, also recommended in the original paper, we use this double zeta scheme. So in this method, we include C0 and C1. We just do this once to get C1, okay. But actually, based on my own exploration, in many cases, even with a single zeta concentric localization, which means we stop here with this C0 only, you can also get satisfactory accuracy in a lot of cases. So by doing this, so now we further have a partition of the virtual space. So now the wave function in DFT calculation will only use the orbitals for the active system, the OS and the VS here, while the rest will be treated as frozen core and frozen virtual orbitals in a correlated wave function calculation. So let's take a look at the entire general procedure. So first we do a low level, typically like a DFT calculation for the entire system. And then, so at this point, the system is not partitioned yet. So everything is treated uniformly. And then we introduce a partition of the occupied space based on the predefined active system and the environment. So now the occupied space has been partitioned. So if we are doing DFT in DFT embedding, we just perform the embedded DFT calculation with this with these two sets of orbitals, and the environment occupied orbitals will be fixed and provide like embedding potential. While if we are doing wave function in DFT, then we actually perform a Hartree fork calculation first using the system virtual occupied and the full virtual, and then we truncate the virtuals using the concentric localization scheme. Then we can do the wave function in DFT embedding calculation, just using the OS and the VS, this active orbital here, and the rest will be treated, will be kept frozen. Okay, so I have probably talked quite a lot about the theory, and now I would like to switch to more like practical aspects. So first, I would like to give you an overview of the functionalities currently available in Q-Chem. So first, we have DFT in DFT embedding, and the typical setup will be you have a hybrid, like a more accurate hybrid functional embedded in a less accurate, like a pure functional, which are computationally cheaper. So with this DFT in DFT embedding, typically it can reduce the computational cost of the compared to doing hybrid functional calculation for the entire system, because you only need to do the high-level fork matrix build using the electron density of fragment A. So it is a much sparser object than the full system density. But the crossover point might come pretty late, and that is probably because Q-Chem's exact exchange calculation, the K matrix build, is also pretty efficient. So you may need quite a large system to actually see the like when this DFT in DFT embedding beats the full system hybrid functional calculation. And we also have TD-DFT in DFT embedding. So we can do, like, for example, time-dependent Chem-B3-Lib calculation embedded in like a PBE environment. So in these kind of calculations, excitation amplitude only consists transitions from active system occupied to the retained virtuals. It can be the full virtuals if you don't do the truncation, but if you truncate it, the virtuals, it will only include the singles amplitude to those included ones. And we have wave function in DFT embedding, and this is probably the most useful feature. For example, we can do CCSD T embedded in like a DFT environment. This is for ground state, and Q-Chem also has many correlated wave function methods for excited states. So we can do embedded EOM CCSD in a DFT environment as well. I will show you some examples for this. And here, as I mentioned, the environment occupied and those excluded virtuals will be treated as frozen core and frozen virtual orbitals in the wave function calculation. So that can significantly reduce the cost of these wave function methods. And I also should mention unrestricted calculations is available in Q-Chem. I mean unrestricted embedding calculation. So we can treat systems like radicals embedded in a closed shell or even open shell environment. But some cautions actually is needed for these unrestricted calculations. This is mainly because this is relatively new and it hasn't been extensively used yet. So yeah, you might need to pay some attention if you find some issues. Probably just email me. Okay. Then I want to talk a little bit about I want to give an overview of the job control keyword of these embedding calculations. So first, as I mentioned, we need to partition the system. We need to, so this will require a fragment input format. I will show you many examples later. And so the first fragment, so for each fragment, we need to specify the charge and the multiplicity. So by default, the first fragment will be the active fragment, the embedded one while the others will be the environment. But this can be changed through this embed fragment input section. And this embedding calculation is turned on using this gen SCF main embed equals true. So the low level theory is specified using this environment method keyword in the RAM section, while the high level theory is just specified using the standard method keyword. And by default, we have this linear approximation turned on, so that is controlled by fixing V embed. That means you just compute the embedding potential at the beginning of the calculation, embedding calculation, and then keep it fixed. And we have spade partition and concentric localization, which can be turned on using these two keywords. And they are currently not turned on by default with the current default RAM settings. But yeah, as I mentioned, I do plan to change this to default recently. And the double zeta option for the concentric localization is currently used as default, and but this can be changed by using this like a keyword. So if you set this to 1, it will become single zeta. And also the projection basis, by default, it is the same as a working basis, but this can also be changed using this concentric rough basis keyword. And so for this keyword, actually the general basis option is available. I will show you one example of that too. So let's look at some job setups. So this is a simple ground state DFT in DFT embedding for a simple molecule, which is ethanol. So here, this OH hydroxyl group, including this sigma bond, will be treated as an embedded active system, and it's treated using the B3-lib hybrid functional, while the rest, these carbons and hydrogens, will be treated using the PBE functional. And here I did turn on the spade partition. So first, in the Q-Chem output, you can see some print of the summary of system partitioning. So here it's saying we have 2 fragments as specified here, and the embedded fragment by default is the first one. And for each fragment, we have 5 and 8 occupied orbitals. And this is the number of basis functions for each fragment. And after we do the partition, we have 5 active occupied orbitals for this OH part, and 8 for this part will be fixed. And the virtuals for DFT in DFT embedding will not be truncated. So in the output, you will see 2 converged SCF energies. And so the first one is SCF energy converged for the low level theory. Here it is PBE, yes, PBE functional. While for the embedded calculation, and the second one will be the actual embedded SCF energy. And yeah, the second one is the one you really want. And at the end of the output, it will also print out the orbital energies. And you may find that the occupied orbital energies are not ordered by their energies. And this is because we have this ordering in this in the MO coefficient matrix. So we start with the fixed orbitals for the environment, and then active occupied orbitals, and then virtuals. So we do this mainly for the convenience of wave function in DFT embedding, because then we can treat all these as frozen core orbitals. And here I plotted the 5 occupied orbitals for the active part selected using the spade method. The first one is the 1s orbital of oxygen, and the rest are the valence orbitals, which are mostly localized in this region. But they do have some tails extended to the environment, which is completely normal because these tails are needed to make sure the orbitals of the two fragments are orthogonal. If the orbitals are absolutely localized on these fragments, then they will not be orthogonal to the orbitals on the other fragment. So this is then we are going to look at like a input for like a wave function in DFT embedding. So here the system is a water dimer. So here I used this input section to specify that fragment 2 will be the embedded fragment, and it's treated using the CCSD method, and the fragment 1 is the environment, treated using B3lib. And so I should mention that in Q-Chem's implementation of this method, we enabled the orbital gradient of SCF, of the embedded SCF calculation. So we can use gradient-based SCF algorithms, such as the GDM algorithm. This is particularly useful for unrestricted calculations, because in those cases, the SCF convergence is much more difficult and tricky. And here I also used this general basis option for the projection basis in the concentric localization. So here it's this is a customized projection basis in this original paper of the concentric localization method. So this basis is much smaller than the working basis here. So using that, you can achieve a more ambitious truncation of the virtual space. So first, you can further reduce the cost. But probably you need to actually stick with double zeta CL localization. And so the final energy reported will be the embedded Hartree-Fock in DFT energy. This is the SCF part, then plus the CCSD correlation energy. So I want to show you an application example of this ground state embedding calculation. So this was an example from the original paper of the space partitioning scheme. So this is like a Manchutkin reaction. So it is a simple SN2 reaction, but now it is in a complex environment, because people find that these reaction barriers will be lowered by this carbon nanotube, this confined environment, which is an interesting observation. And here we just use QM embedding method to model this environment. So the reaction and the partition of the system here is very natural. So the reaction complex will be the central system, and the carbon nanotube will be the environment. So here are some of the results. So here are all the high-level calculations embedded in this blib environment, and here the blib data just serves as like a blank control group. And all these calculations are done with a quite small basis, because I do need to get the results quickly for this talk. So then here we so here we can see the barrier height do have a quite like a large spread. Okay, so we can see that the 3 wave function methods consistently give higher barriers than DFT. So among the DFT method, this DFT method, the omega B97 omega B97 M-V functional actually has the highest barrier, but it is still quite far from the wave function numbers. Also, these calculations are done using this tiny little basis, so they may not reflect the actual accuracy of these methods. However, this trend makes a lot of sense, because it's known that the barrier height calculation is difficult for DFT, since in the transition state, typically I think, yeah, I might have a network issue. Sorry about that. Yeah, so yeah,
we can hear you now.
So this, sorry if I repeated something I just said, but But here the trend do make sense because the DFT suffer from self-interaction error more for this transition state. So you can see here the B-lib functional does give the lowest barrier, and then with more like exact exchange, you get slightly better. So we also checked the single versus double zeta concentric localization for these correlated wave function methods. And here you can see if you just use the walking basis as a projection basis, you essentially see no difference. So yeah, so here the single zeta basically gives the same numbers as the double zeta concentric localization. Okay, and I also want to mention application from my own research, which is related to this code development. And here we are doing electric field calculations in complex environment. So the goal of doing this, is to calibrate the vibrational Stark probes. So let me tell you more about that. So we are going to calculate the ensemble averaged solvent electric field on chemical bonds. So to get an ensemble, so first we sample the solute-solvent configurations using molecular dynamics. Okay, and then we truncate these MB frames to get the solute-solvent clusters. And then we can compute the solvent, the electric field arising from the solvent electron and nuclei on these chemical bonds. And here we used this state partitioning method to calculate the environment field on the solute atom positions. So we can get the electron densities from the environment, and then we can get the electron densities from the environment, then calculate the electric field on the atomic nuclei of the solute part. And then for each chemical bond, we just compute the average of the electric field projected along the bond direction on the two bond atoms. And yeah, so that's a definition of the electric field on a chemical bond here. And so we do this for a lot of MD frames for each solvent, and we get the ensemble averaged solvent electric field. And we can repeat that with a variety of solvents, and that will give us a field frequency correlation based on the vibrational sorbitochromism. So here are the field frequency maps we got. So here's the vibrational frequencies actually obtained from experiment. So this work is done with some experimental collaborators, and here's the electric field, the x-axis from our calculations I just told you about. So once these vibrational Stark probes are calibrated, they can be experimentally put into some unknown environment to probe the magnitude and even orientation of the electric field. So one just need to measure the IR frequency and then use these linear correlations to figure out what is the magnitude of the electric field. So this is a pretty powerful technique. And here I didn't really need to do any like a true embedding calculation, but I did do this using the embedding code. So because the electrostatic catalysis is currently a pretty hot research topic, so I would like to show this example to give you an idea how you can do this using Q-Chem's embedding code. So here we do this using two input jobs. They just need, so the second one need to be right after the first one. So here we calculate the electric field on water 1, this fragment 1's nuclear positions, and this is controlled by ESP grid equals 0. That means you are looking at the calculating the ESP, electric static potential, and also electric field at the nuclear positions of the fragment 1. And to do this, we started with an embedding calculation, and so here we first do the calculation at the low level, the B3 lib method. Then we do the state partition But here I put in an early stop keyword that will terminate the first calculation when the partition of the occupied space is achieved. So it's more like a served. It's more like served as like a post convergence processing, like an orbital localization. You can also think that way. Okay. And so by doing this, you can skip the rest of the embedding calculations, which can save quite a few, like a fork matrix build. And then in the second job, I used this ghost atom trick. This is because we need the nuclear positions of this first fragment, but we only want the electron density from the environment. So we only want to calculate the electron density using the orbitals from the environment. So this can be done just by using this ghost atom trick. So in this calculation, the number of electrons is equal to the number of electrons for just a 1 water molecule. So all these, the environment occupied will be selected as a occupied orbital for the second. And yeah, this does read in the MO coefficient computed by the first one. Okay. And now I'm going to talk about some excited state applications. First, let me introduce how to set up these jobs. So this is like embedded TD-DFT in DFT calculation. So here is so here it's doing the TD omega B97X-V in this PB0 environment. So it was mentioning that so in Q-Chem 6, we have the analytical second functional derivative of this functional containing the VV10 non-local correlation. So this TD-DFT calculation can now be done fully analytically. And so here, as I mentioned before, the environment occupied and excluded virtuals do not contribute to the excitation. So the dimension of the singles amplitude will get reduced. And we also, so here I tested the single versus double zeta concentric localization. So for both of them, they have the same number of active occupied orbitals, while the number of active virtuals are different. And it's doubled with the double zeta concentric localization, of course. And so you can see that for the first excited state, these two do not really make a difference. While for the second excited state, there is quite some difference in the excitation energy. And this is because if you look at the use some wave function analysis tools to analyze the second excited state, you can see its virtual is very diffuse. So this state is not really suitable for embedded TD-DFT calculation or any like embedding type method. But for the first state, it's a well-localized valence excited state. So it's I can do like a NTO plot for this calculation and generate the natural transition orbitals. And so from the dominant NTO pair, we can see it's a typical N to pi star excitation. And we also have wave function in DFT excited state calculation. And this is the job setup for embedded EOM CCSD in the DFT environment. So here, the job requests 2 EOM EE CCSD states, and the transition properties are also requested, and that includes things like oscillator strings, transition dipoles, and also natural transition orbitals if you have NTO pairs greater than 0. And I also checked the single versus double zeta CEL truncation, basically same story here. So here I also used this, turned on this state analysis keyword, and this will trigger the analysis tools available in libwfa. So it's a very useful library for wave function analysis. It can generate plots for transition density, electron hole density, difference density, and also attachment detachment densities, all these things, as well as natural transition orbitals. And it can also print out other descriptors of excited states, such as atomic charge populations and the charge transfer numbers. So it supports, besides UMCCSD, it also supports TDDFT and ADC-based excited state calculations. And here I have this WA level equals 4. It is required to generate this NTO, natural transition orbital cube files. Okay, so here are some of the plots I generated using this libWFA, including the whole electron density and also the dominant NTO pair. So I want to talk about one application example from my own research. This is some embedding calculation of the GFP chromophore in a aqueous, like a water environment. So these calculations are done with these truncated GFP water clusters, and they are carved from like MD frames with a 6 angstrom cutoff radius. That means for each water's oxygen atom, so if it's within 6 angstrom of any of the QM or no any of the like a chromophore atoms, then it will be included as part of the environment. And here we do the UMCCSD calculation embedded in PBE0 environment for water. So first we want to check if the 6 angstrom cutoff is good enough. So we did check. We use this embedding. We did embedded calculation with for the clusters with a slightly larger cutoff radius, 7 angstrom. Also, these two calculations should have the exact same number of occupied and virtual orbitals after you do the space partition and also the concentric localization. However, the calculations for the 7 angstrom cutoff clusters still like notably more expensive simply because these clusters are larger and contain more atomic orbital basis functions. But luckily, I think the results are close enough. So probably 6 angstrom is good enough for us already. And also, these calculations are done with this 601 plus G star basis, pretty small basis for correlated wave function calculations. But currently, we can only afford, even with this basis, we can only afford single zeta concentric localization for the embedded UMCCSD. Using the computational resource available. Since we are running this calculation on the NERSC cluster, and if you have used NERSC, you know there is a 2-day time limit. So we need to do a lot of things to reduce the computational, try to make the calculations cheaper in order to fit in this 48-hour time limit. So here we use the surrogate method, like a embedded TD Chem B3lib calculation to test the effect of this concentric localization approach, like a single versus double zeta. And you can see, as some of the examples I showed before, it doesn't really make a big difference. So doing single zeta is fine. And finally, we also checked the embedded TDDFT versus standard TDDFT. And we need to be more careful here because this is not really an apple-to-apple comparison, because in the standard TDDFT, you included some more excitations from such as like a chromophore to solvent charge transfer excitation, which are not captured at all by the embedding approach. However, I think in general, there is still a pretty strong correlation, and usually the standard TDDFT gives slightly lower excitation energy. So the whole point of doing this is for a machine learning project, using machine learning model to predict linear and multidimensional electronic spectra. So these machine learning models are used to map these solid solvent configurations to the associated excitation energies. And then by doing that for a time sequence, we can calculate the energy gap correlation function, and then we can use a dynamical dynamics-based method called like a second cumulant expansion method to calculate the linear and multidimensional spectrum. So previously in the Markland group, people developed like a machine learning model to map these configurations to TD-DFT energy gaps. But these TD-DFT energy gaps, and using the energy gaps predicted using the machine learning model, we found that the predicted linear spectrum for this GFP chromophore in water is too narrow compared to the experiment. And we wonder if that is caused by the insufficient level of accuracy of this electronic structure method. So here we developed a transfer learning model to, so first we start with this TD-DFT network and then refit that to 200 embedded CCSD calculations I just talked about. And this gives us this like a refitted neural network model. And with this transfer learning model, we can actually get a much better agreement with a linear spectrum from experiment. And this is probably because this excitation in the GFP on the GFP chromophore has partial intramolecular charge transfer character, which is a big challenge for TD-DFT. And also this broader spectrum by the CCSD method can also be hinted from the energy, this correlation plot for the excitation energies of these two methods. You can see the spread of excitation energies with CCSD. Embedded CCSD is about twice as large compared to TD-DFT. So you can expect from a static point of view, it should give you a broader spectrum. So to conclude, I talked about the projection-based embedding method in Q-Chem. This method offers an effective approach to describing the environment using quantum mechanical methods. And the success of this method is underpinned by Q-Chem's large collection of wave function and DFT methods for both ground and excited states. And we do have quite a few features planned, and I do hope to enable at least some of these in the near future. So first, we want to include the outer environment using even lower level method, such as implicit solvent and a QMMM type method. So currently, probably fixed charge QMMM can already work with the embedding code, but currently we have some issues doing implicit solvent, and we need to fix that. And we would like to support many other useful functionalities in Q-Chem under this embedding framework, including the orbital optimized DFT for excited states, constrained DFT for a charge localized diabatic states, and energy decomposition analysis for studying non-covalent interactions. And I also would like to explore the possibility to do this projection-based embedding using absolutely localized molecular orbitals. And Jason Goodpaster and co-workers have actually explored this already, and they found the results pretty promising. And since Q-Chem has a ready code for almost, so this should be very easy to implement. And finally, as we would like to enable nuclear gradient for these projection-based embedding calculations. This is not a trivial task, but it is possible to do. Okay, thank you very much. And I would like to take your questions.
Thank you, Yuezhi. This is a really interesting and informative talk, and thank you for preparing that. We don't have questions right now, but one of our listeners pointed out that your internet was interrupted in the middle of the following sentence. I'm going to read that. DFT underestimates the barrier because transition states are typically, and you're interrupted after that. So would you?
Okay, yes, I will go back to that. 1 second, please. Okay, yes, here. So yeah, I would like to say what I wanted to say is probably so. So here we notice that DFT method systematically give lower barrier heights compared to these wave function methods, and this is like a well-known problem because these transition state structures are typically born like plagued by self-interaction errors, and then these errors are not really cancelled out when you calculate the barrier height because the reactant state is not impacted as much by the self-interaction error. So that causes a well-known problem for DFT to like underestimate the barrier heights.
Thank you. Okay, now we have questions. It's from the same listener. Nice talk. I wonder how embedding would help the E-field calculation. Was the solvent treated by the low-level theory?
Oh no. So this is so as I mentioned here, like I didn't really do an embedding calculation because here I really don't have the need. So as you can see here, the method and the environment method are exactly the same, and the method, the high level method here even doesn't matter because we put in this early stop keyword to just terminate the calculation after doing the spade partitioning. Yeah. So yeah, typically I think there is I don't really see a need to do the to treat the environment and the the solute at different levels of theory and in this kind of calculations. I basically just borrowed this embedding code I developed, and I realized, yeah, with this code we can do this task easily. So that's why I talked about this here.
Thank you.
Yeah.
So I don't have more questions because we're a little bit over time. So yeah, so since we're over time, if you have questions later, or you watch the video through YouTube, so feel free to send us an email. I'll make sure they're answered or forward to Yuezhi. So I'm gonna move to close the webinar. So I'd like to thank Yuezhi again. Thank you for this amazing talk, and also like to
my pleasure. Yep, of course.
Thank you. And also like to thank our listeners, and so the video should be posted on YouTube in the next couple of days. So this concludes our webinar. See you next time. Bye.
Yeah, bye.